Hello class, my name is Valeria Proano. My team members are Ruocco and Javier Gutierrez. We are team 15 and we are going to work with a power transmission system and we're making a speed reducer. The requirements for our project is to make a power transmission system that can sustain 8 horsepower. The input and output has to change from 800 RPM to 40 RPMs. And the direction of the input and output shaft must be opposite, parallel, and aligned. We have to achieve the smallest volume and weight we need it for a high precision application. It must endure light shocks, operate at room temperature, and the cost should not be a parameter. One of the parameters is not critical. Also, the components have to be in the market, and we're going to use Boston Gear and SKF catalogs.
This is a layout of our transmission. As you can see, it has 4 reductions and a set of idler gears. We had 2 main issues when designing this layout. The first issue was alignment. We had to run different trials so that the input shaft would be perfectly aligned with the output shaft. What made this even harder was the fact that the revolutions had to be opposite. This is the reason why we made this idler gear set. The gears have to be selected from the Boston Gear catalog. This catalog has all the detailed information and specs about each gear that they manufacture. The gears have to be selected based on their horsepower capacity, RPMs, and number of teeth. This is an example of one of the tables found in the Boston Gear catalog. Based on the RPM, as you can see here, you can go down and select the correct gear based on the horsepower that you need. Then you can find the number of teeth, and then you can go to a different section, a different reference page that has all the detailed information about that specific gear.
Okay, shaft analysis. Basically, for the shaft analysis, the first thing you have to do is, already having selected the gears, you're going to have your radial and tangential forces. With those tangential forces, what you're going to be doing is you're going to calculate the reaction forces at the support points. What you want it for? You're going to want to calculate the endurance limit. To calculate the endurance limit, there's many modifying factors: Ka, Kb, Kc, Kt, and Ke. These factors depend on size, temperature, reliability, and other different factors. After you calculate your endurance limit, you're going to want to test the system. So you're going to want to apply the Goodman modified equations. For this, you're going to have to find first the von Mises stress, and after that, you analyze your system. For our shafts to properly work, we had to use different materials. So we used 1018 for the first 3 shafts and the last one, and 4130 steel for the shafts 4 and 5, which are the shafts that are under critical stress.
Now we're going with the bearing analysis. We picked single roll ball bearings due that we only have spur gears and we only need to take radial loads. Now the gear size determined the board diameter. So we picked this board diameter in inches and we looked them in the catalog and we chose bearings according to that diameter. We got the catalog number and then we compared to the C10 calculated for each bearing. The requirements and assumptions for these analyses were the weighable parameters, the life to be 10e to the 6th, reliability to be 95%, and we picked the desired life of 14,000 hours. A desired load was according to the shaft, to the reaction forces in the shaft, and with this process we were able to achieve 100% reliability in all the bearings. Now for the bearing selection, this is a graph that we have a table with all the bearings for shaft 1, 2, and 3. We did the same process for the other shafts. We calculated first the C10 through this formula, and then we got, for example, 2 kilonewtons. Then we got the number from the catalog for the bearing that we picked, for example, the RMS 6, and then we calculated the reliability and gave us 100%. Now we're gonna go with the application. The application that we picked for our transmission unit is we're gonna have a generator connected to a turbine, but we're gonna need a speed reducer because sometimes we don't know if the water flow makes the speed of the turbine way higher than what the generator can take.
This is a video of an animation of our power transmission unit design. Basically, in the elaboration of this project, we learn how different components interact and how one affects the other. We also perform a failure analysis for the entire unit and all its elements. We obtain factors of safety greater than 1 for all of the components, which makes our power transmission system design very reliable. We hope you enjoyed our presentation. Thank you.